All right, so what I did up here is to move along, want to look at some series resistances. And as we had up in the classroom the other day, we had 8K, 8K, and 8K. And overall, the overall resistance was 24 K ohms. And that's great. One of the things that we're going to look at and start to develop is a greater understanding of how the voltages are developed across resistors and what's happening there, because we haven't explained it yet, haven't talked about it, but as we start to have current flow through these with the amount of resistance, this thing is going to have an opposition which is going to build up a voltage potential over it. And this one will build up a voltage potential based on that same current, and so will this one. Now, in a series circuit, as you will see, the series circuit, remember this, it has the same current throughout. Okay. Whatever the current is here, is the current is here, is the current is here, is the current is here. It's the same current all the way throughout. To find that current, what we need to do is overall find the total resistance. In this case, I've got 3 resistors in here, R1, R2, and R3. Now, all we have to do is look at these resistors and add them up. They're in series. They share all the way through. There is no other paths. There's only a single path. So they all add up together to be one overall resistance. So I would say that the RT, total resistance, is equal to R1 plus R2 plus R3. And if I had R4, R5, R6, I could just keep on going. So, you know, they would say dot, dot, dot to R to the n. However, in this case, we just have 3 resistors, and therefore it is going to be equal to 680 ohms plus 1.5 K ohms plus 2.2 K ohms. In this case, the overall resistance is going to be 4.36 K ohms, all right? So I've got a total of 4.36 K ohms. Now I can look at the circuit slightly different if I wanted to, and I can say, well, isn't that the same as doing this? Having 12 volts here and 4.36 K ohms, RT, VS. Well, yes and no. Electrically, if I put these in a black box and put this in a black box and measured it as resistance, I couldn't tell the difference. However, the power dissipation overall may be slightly different that it can handle, and maybe not, just again, depending upon the sizing of the different components. But in this case, I would have 4.36 K ohms here, 4.36 K ohms here, and at that point, I want to find out how much current is flowing through this thing. Well, to do the current, again, looking at voltages and everything else, I am going to say that the current, I, is equal to the voltage divided by the resistance. Overall, the total current is going to be based off of this total resistance, not any one individual one, but over the overall total. So that means it's going to be 12 volts divided by 4.36 K ohms. And in this case, it will be a total current of 2.74 milliamps. Right. Now that means 2.74 milliamps here, 2.74 milliamps here. But this is not our circuit, and it's just a representation of the overall. If I transpose this over here, that's 2.74 milliamps here and 2.74 milliamps here. But that also means that there's 2.74 here, right? And here. Because it's all the same circuit, all series circuit. Again, we don't add them all up together because it's the same. And now we should be looking at this a little closer, because we have 12 volts applied, and we have 2.74 milliamps of current that flows through each one of these resistors. Since there's so much resistance of each one and so much flow, we're going to develop a potential voltage across each one of these. And some people are going to call it a voltage drop. And that's perfectly fine in many ways. It's slang for us. We're going to drop a voltage across it. We're actually going to develop a voltage across it. So that's a little different in thought, but that's what we're really doing. To develop that voltage across each one of them, as you'd see that we would literally take the amount of resistance, multiply it by its current to find out the voltage across it. Take the resistance, multiply it by its current, figure out the voltage. Take the voltage, or resistance, multiply it by the current going through it, which they're always the same, and figure out the voltage. So in this case, when I do that, I'm going to see that I have 1.86 volts developed across R1. I'll see that I'll have 4.11 volts across R2, and across R3 is 6.03 volts. Now that's kind of weird. 1.86 and 4.11 and 6.03. And in reality, I'm looking at 12 volts. So how does that happen? Well, this is called a voltage divider. And we're going to talk more about how voltage dividers work in a greater scheme of things when I come back. But I want you to take a look at this. 680, 2.74 milliamps, 1.86 volts. 1.5K, 2.74 milliamps, 4.11 volts. 2.2 K ohms, 2.74 milliamps, 6.03. What did we say when we talked about the voltages? What happens to voltage if current stays the same and the resistance changes? As the resistance increases and the current stays the same, that says the voltage must increase. Now this overall supply voltage hasn't increased, but notice what's happened to the voltage developed across it. The 680 was 1.86 volts. The 1.5 K ohms is 4.11 volts. And the 2.2 K ohm is 6.03 volts. Well, that's what's happened. As the resistance is increasing and the current is held steady, well, the voltage increases. Now, again, it still doesn't make a whole bunch of sense until we look at these out and think about it this way. I have 1.86 volts plus 4.11 volts, which gives me 5.97 volts. And 5.97 volts plus 6.03 volts gives me 12 volts. The voltage that's being applied to all of these must equal the sum of all the voltage being developed across them. And that's a series of resistances. It gives us another check. It gives us some other opportunity to do other things, such as making step-down voltages, step-up for certain things, and creating certain biasing circuits. But really, that's about what happens. We're going to take that current, that resistance to find the voltage. That current, that resistance to find the voltage. That current, that resistance to find the voltage. Voltage, voltage, voltage added together must equal our supply voltage. If it does not, there's a check for us. First of all, we've got our current going, we've got our overall total resistance in there, and we can figure out all that. And again, if we look back here at 12 volts and this resistance, we know that it's that much current. So we have a couple built-in checks back and forth. Now the one thing that we haven't done yet is look at power with this. And that's fine, but we need to find out what not only is the power being produced by any one of these, but the overall power being consumed. And if we look at that, we can use the power of just taking the voltage is equal to the current times the resistance. And when I look at R1, I'm going to see that's 5.1 milliwatts, right? 5.1 milliwatts. And this one, well, what happened to my resistance? It's almost doubled. So I'm going to see about 11.3 milliwatts. That makes sense. I've kept the current the same, increased the resistance, which means my power dissipation must have increased. And the same thing here. If I increase the resistance once again, kept it there, I'm going to see 16.5 milliwatts. Right? Fine and dandy. I could use a quarter watt resistor here, a quarter watt resistor here, a quarter watt resistor here. No problem. However, I want to know what the overall power is being utilized here. Well, all we do is add them together. So we have 5.1, 11.3, 16.4, 16.4, and 16.5. That's approximately 33 or 39.2 milliwatts. 32.9 milliwatts. Total power. All right, that's what we say it is. We've got the voltages, we've got the currents, we've got these powers for each one of these. And we say the total power, again, power total is equal to power of R1 plus the power of R2 plus the power of R3. And that says 32.9 milliwatts. Here's the fun part. If I say I need a check, a major check, I've got this voltage and I have this current, this resistance. I can figure out what the overall total power should be dissipated just based on those two numbers instead of just adding those all up. And I'm going to see that that number is going to be 32.9 milliwatts, right? Because power is equal to E R and is E squared over R. Well, using that is 32.9 milliwatts. And that's what we got from adding them all up and figuring them out individually. So if I added them all up individually, came up with that number, and then I used that number to find out as a check, I would suffice to say that you got it all right. Now, the biggest issue that we have with this board here is that it's jumbled up. I've got everything written up here where you really should be taking the time to do it step by step by step by step all the way through. Figure out what's happening here, figure out what's happening here. And you may have to say just R1 and I1 and IR2 and IR3 all the way through. But it will work out. Take your time and you'll get it.